This is the first video in the linear algebra series. It's about matrix creation, manipulation, and arithmetic. Let's get started. Okay, I'm going to assume that you have looked at the Learning Maple video on vectors, Cartesian coordinates. So I'm going to go from there. We're going to make a matrix here, and we'll call this M. And to make a matrix, one of the easiest ways is to go down to this matrix palette and then basically select a matrix. So you can select one. I'm going to drag it down to a 2 by 2, and then when I click Insert, I insert it there, and now I can fill numbers in. 1 tab, 2 tab, 3 tab, 4. And that's one way of making a matrix. Another way to make a matrix is to not use the palettes and rather just go by rows. 1, 2, 3, that's the end of that row. Then 4, 5, 6. And that's the end of that row. And there's your matrix there. Of course, you can also make it with parallel vectors. M is actually a matrix made up of the vector 1, 2 with 3, 4. So those two vectors are in parallel, and it produces that particular matrix look. Okay. Of course, obviously, you should be able to use the matrix command. So M is a matrix. It is a 2 by 3 matrix, and the default will make all the elements 0. If you want to make it filled with ones, M1 is a matrix, which is again a let's make it a 3 by 3 matrix filled with ones, and now it's filled with ones. And then finally, of course, you can make a matrix out of a list of lists. M is a matrix for which we're going to list, and in each list we'll have each row, 1, 2, then 2, 4, and then 3, 0. And then we'll make that matrix there. Finally, sometimes it's useful to use a function to generate a matrix. So what you can do here is you can create a function. So let's say we're going to have 3 by 3 here, and we're going to create a function which is going to take the information about the row and the column, and it's basically going to calculate row minus 1 times n plus column. And that's going to be our function. So M is now a matrix. It is an n by n matrix. And it uses the function f to fill the numbers in. And it does something like that. Finally, the last thing that's kind of useful here is you can use random numbers to generate a matrix. M is a matrix. It is a 3 by 3 matrix, and I'm going to use the random number generator from 0 to 5, and that will fill it in with random numbers. There's also a random matrix procedure, which is much faster, that is built into linear algebra. Now, you probably remember a little bit about how to index vectors or matrices. So let's actually give ourselves a little bit of space here. For example, let's make V a vector which is A, B, C, and D. So again, oops, you got to put the D in there. And so let's remind ourselves how we refer to any element within there. So let's say if I want the second element, that would be V2, and that pulls out the second element. If I want the second through the fourth element, I want 2 range to 4, and that pulls out the second through the fourth element there. Well, matrix indices is pretty much the same way. Again, let's build ourselves a matrix, which is kind of useful. Okay, and I'll make it out of A, B, C, D. That's the end of one row. And then E, F, G, H, I. That's the end of the other row. And then, oh, here we go, J, K, L, and M. And since I put it that way, it does look like the matrices. Whoops, too wide or too narrow. What did I make a problem? The problem is I have too many elements on line 2. So a good time to check to make sure that you have an error. So I should actually only have 4 on each line. And that fills in that right there. So again, how do I refer to an element within a matrix? Well, I can say M. And I want the second row, third column element. And that's G. Second row, third column. Okay. What if I want the second row but the first 3 elements? Second row, first to third element. And that's E, F, G. Okay. What if I want everything in the line of the first row? M, first row, every element. Or if I want everything in the first column, every element in the first row. And maybe we'll fill in the fact that you're going from the one extreme to the other. Okay. Finally, it's kind of useful to actually use the sequence command in this type of manipulation. For example, what if I want to list out every row separately? So I want to sequence M. N is going to be our counter of each row. Every element in the row is listed there, so that's every column is going to be listed there. And again, N is equal to 1, 2, and it turns out we have 3 rows, so we'll put that in, and it will list out each element, or each row separately. One of the more useful procedures in the linear algebra package is equal. It allows us to check to see if 2 vectors or 2 matrices are the same. And the way to call it is to say linear algebra :dash equal. And you can ask the question, is A equivalent to A? And the answer will be true. We can do the same thing and ask, is A equivalent to B? Now, it's clearly A is not equivalent to B because they're not even the right dimensions, and so it will turn false. But if I ask the following question, linear algebra, is A equivalent to B from 1 to 2 and 1 to 2? That means only the left-hand side of the matrix. The answer is true. Okay, let's get into some manipulation of vectors and matrices. I'm going to change the imaginary unit symbol from large I to small I. Small I will now represent the square root of -1. I do this because I'm a physicist. I've created a vector which is A, B, C, and I. Of course, Maple doesn't know anything about A, B, or C. They could be complex variables. And then I've also included a matrix as listed here. So how do we transpose these things? Well, the long way is to actually call the linear algebra package procedure, transpose, linear algebra :dash transpose, and then we give it the vector. And so it returns a row vector. It does nothing about the fact that we have an I there, and that's what the output is. We can do the same thing with M. Okay, linear algebra :dash transpose of M. And as you can see, the rows and columns have been switched. The 2i is now at the bottom, the 3 is now at the top, etc., etc. That's kind of the slow way of doing it. Most of the time, what I prefer to do is to use the shortcut, and it's quite readable, the %t. And again, this will turn this column vector into a row vector. And the same thing works for the matrix, swapping the rows for the columns. Now, many of you probably want Hermitian transposes or complex conjugate transposes. Sure, one could write out conjugate, applying it to every element of the V transpose %t. and that will produce that character there. Now, the problem with that is, again, Maple doesn't know anything about A, B, and C, so let's give it some help, and let's tell it, assuming real, and now it will return it. And all it's done is changed I to minus I. The same thing is true with the M matrix, but that is much too cumbersome. So instead, Maple has provided a Hermitian Hermitian transpose shortcut, and that is V to the percent H. Same problem, of course. Just all we have to do is tell it assuming real, and again, it's taken the row column vector and it's turning into a row vector, and it's also done the conjugate on every element in there. And the same thing works for their matrix. Okay, we get the same transpose, but now you can see from up here to down here, all the i's have turned into minus i's, and of course minus i's have turned into positive i's. That is usually the best way of doing it. Let's give ourselves some space, and we can play this manipulation also with a matrix inverse. So let's say you want to do the inverse of the matrix. Well, again, you could call the linear algebra :dash matrix inverse procedure, pass it M, and it would return this output here. We'll call that M, okay? But I find what is even easier and, again, more readable is to the shift 6 minus 1, and we produce the same inverse. Let's see if this truly is the same inverse, because the inverse with itself, when multiplied, period, M, should produce the identity matrix, and it does. Or M, period, M to the minus 1. And if you put the M in, sometimes it actually recognizes this is a matrix or vector multiplication. So that makes life a lot easier there. Finally, involving manipulation, it's useful to be able to create your own vectors and matrices out of functions. I have created two here. They're pretty straightforward. If I call f, which is a function that creates a vector, and I pass it something like y, it substitutes y in for all the x's, and now I get a column vector with y's involved. And I can do the same thing with the z function of a matrix. I just pass it something else. Let's pass it actually alpha. All right? And as you can see, we swap all the thetas with alphas. It's time to do some arithmetic with our matrices. I have built some matrices in a vector already. This vector is kind of interesting. Essentially, every element of the vector is labeled by the subscript n. So each of these elements, that's the v1 element, that's the v2 element. I've also created the a using a function which, when passed the row column, will return the a index of row column. And so I use that function to create the matrix. Maple has something like that already built in. If you say symbol equals b, then it returns again all the elements of b, the indices of the b, assuming b is some other matrix. So there we go. There's our matrix A, and there's our matrix B. Let's do some addition here. For example, I can say A matrix plus A matrix, and it, not surprisingly, it adds the two together, and we get two of each of these elements there. I could try A matrix, since that's a 3 rows by 2 columns, and if I add it to B matrix transpose, which takes the 2 by 3 and turns into a 3 by 2, then you can see how it is adding those particular elements. But of course, if you do try to add a 3 by 2 to a 2 by 3, Maple will get very cranky because the dimensions do not match, and it will note that in the calculation there. Let's do some multiplications here. We'll zip up and give ourselves some more space. Okay, so what if I do A matrix period V, and notice again Maple says, oh, you're going to do a vector or matrix multiplication. When we do that, it figures out how to do the multiplication properly with a 3 by 2 by a 2 by 1. Okay. Here's another multiplication, A matrix. Since this is a 3 by 2, I can do it a period of B, or I can go down here and select this button, B matrix, and it will properly calculate all the elements of essentially this 3 by 3 matrix together. And we can do the opposite in a B times A. Now that I've done matrix multiplication by standard multiplications, let's do element-wise operations. I've created myself another matrix, which is also a 3 by 2, just like the A matrix. So if I wanted to say A matrix, which is a 3 by 2, and multiply by C matrix to the percent T, then it will properly do that calculation out. But let's say I want to multiply the first element of C with the first element of A, then the second element of C with the second element of A, and et cetera, et cetera. So I want to do each operation individually. So what I want to do is I want to take A matrix and multiply element-wise onto C matrix. And as you can see, the output is the A11 is multiplied by the C11. The A32 is multiplied by the C32. This sort of operation is sometimes useful if you want to put everything like in a spreadsheet type environment and do that type of calculation. Okay, what if we want to do by element-wise, take every element A and divide by the element in C? Well, that's the same as multiplying every element A by the inverse of every element in C. So I can do that by saying A matrix times element-wise C matrix, but I want to do the inverse element-wise of every element, so it's to the element-wise of -1. And when you do, you get this result. If you don't put in the tittle, then it will not work out and you will get this weird error. Let me show you. I'll copy and paste. I'll take out the tilde here. And you'll say the power is not defined for non-square matrices, blah, blah, blah. Again, what it tried to do is actually do the inverse of the entire matrix rather than the inverse of each element. That's why you need to put the tilde in to make sure that each element is done. Element-wise operations on matrix are very useful. For example, what if I want to take the sign of every element within the C matrix? So again, I'd say sign, spelling it correctly, element-wise, every element of C matrix. And it puts the sign there. You can even create your own functions. For example, what if I have a function which is basically just, I don't know, maybe the square root of x. And that's our function. And we want to operate this on all elements within C. So we just say f, element-wise, operating on C matrix. And again, it will work through and take the square root of every element in C. I should finally note that at one time, in order to solve sets of equations for unknowns, you would actually set them up so that they looked very much like the following vector matrix equation, that A times X, where X is the set of unknowns, is equal to B. A are all the coefficients for the X, and B are the elements on the other side of the equation. There are our coefficients, there's our other side of the equation. Well, of course, Maple can do that and actually can create the, dash greater than. Results, if you call the linear algebra colon dash linear solve. You pass it A, you pass it the vector B, and it returns the results. I don't understand why this is necessary, but I demonstrate it. Of course, what you can always do is say, I want to solve my set of equations of equation 1, equation 2, and equation 3 for the unknowns, which it already knows, and it produces exactly the same result. Hi, I'm sorry that was so long, but I hope you got a lot out of it. The next video will be on how to do eigenvalue problems using Maple.